I just want to start by going over some of the homework that you turned in on Wednesday. That just a couple of these things seem to I thought I might clarify a bit. I also want to warn you there's some construction going on in the building here, so there might be some loud noises every now and again. I think they're slowed down a little bit here, but I just want to warn you on that. All right, so the first one was 172, and it seemed like people did pretty well on that one. Basically you just want to find the delta that would happen if the temperature increased to the final temperature, which was 54 degrees, and then look at how much of that delta then the ceiling would prevent. So that is a little bit, might be worth mentioning, is I often look at these problems as though they start at the final temperature. Even though that might be a physically impossible situation, I kind of look at it that way. So I would consider this problem here to start at a temperature of 54, I think it is. And then, obviously, the bar is too long then. So if that's the case, then the ceiling has to compress the bar, not the full delta that would occur on account of that change in temperature, but the ceiling would compress the bar starting with that delta temperature and then subtracting off the gap. Okay, so your delta for stress would be slightly different, or quite a bit different actually, than your delta for temperature. And then once you had that, you could kind of work your way back to what the force was that is required to push that bar to the required length. All right, this one was involved, but seemed like people did fairly well at. So here's the preliminary information, the areas, the strains, and then once you have the strains on account of temperature, you can then find the deltas, and then that leads to an overlap, which is physically impossible, but I consider that to be my starting condition. Okay, so the green there is the overlap, because both the stainless steel and the cast iron try and get longer. So I consider the problem to start with the overlap, then they push back into an equilibrium position, which is different than the position where they started. So what you want to do first is run through all these calculations and come up with the overlap, which is 0.0002436 meters. Once you have that, you realize that equilibrium occurs when they come to rest, and when that occurs, the load in the stainless steel is equal to the load in the cast iron. All right, and then you can find, that delta is PL over AE. So the loads in the stainless equals the load in the cast iron. So that, and if you solve for the load here, you get delta AE over L. So you can equate delta AE over L for the stainless to delta AE over L for the cast iron. And based on that, come up with a ratio between the two deltas. And then once you have that, you know that the total delta is the overlap. So you add the two deltas together to get the overlap, substitute in the 3.193 delta stainless steel for delta cast iron, you can find delta stainless, and then multiply that by 3.193, you come up with delta cast iron. Add those together, you do get the overlap, so that checks out pretty well. Once you have that, then you can find the load in both the stainless and the cast iron, and they're roughly equal. All right, so you know that the overlaps add up, and that works out to 0.0002436. You then know that delta is PL over AE, so you can back solve that for the load. P is delta AE over L, and you can solve for the load in the stainless and the load in the cast iron, which come out to be about equal, so that's a good check on the work. And then given that the forces that the stainless and the cast iron exert on each other will equal the forces they exert on the walls, that will equal the result, the reactions. Okay. All right, now the one after that, we want to do a couple of things. We want to find tau max and sigma max, and that's pretty straightforward there. Tau max is just P over A, and sigma max is P over A, the normal stress, the maximum normal stress, and the maximum shear stress, tau max, is plus or minus P over 2A. So these numbers here I think are easy enough to get. We also then want to find the stress on plane AB. All right, now what we have then are these formulas that we use to do that. They're on your formula sheet. These are the standard axial loading formulas, okay? And those are formulas 21 and 22. Now, you have to know what to plug into that, okay? So we need P, we need theta, and we need A for both of these formulas. Theta is the angle measured counterclockwise from the standard cross-sectional plane. So the standard cross-sectional plane is right there. This angle right here that we could use is, of course, not 26. It's 90 minus 26. It's 64 is what that is. But notice that that is clockwise, so that's going to be negative 64 when you plug it in. Okay. All right, so when we apply these formulas then, we're going to need to have some inputs. Now the inputs are going to be P. Now P is compressive, so that goes in as a negative 6,000. The angle, as I just mentioned, can be negative 64, but you can also come around this way and you can add 90 and the 26 and get 116. You could also come from this horizontal plane. I mean, there's lots of ways to measure it, and you can come around that way, and that will be 180 plus the 116. That's 296. So you could use any of those angles you wanted. Okay. The one I would tend to use would just be the smallest one, which would be negative 64, although 116 makes perfect sense also. That's counterclockwise, so it's positive. All right, now the area is the standard cross-sectional area. Keep in mind that formulas 21 and 22, they do all the trigonometry that we did in class for you. They adjust the area. They start with the standard cross-sectional area, which is what you input, and then use some trig to get the area of that angled plane. And they also then use trig to get the components of the force that are exerted normal and for the normal stress and parallel for the shear stress to the plane. So if you just use these inputs here and plug them into that formulas, which I'm showing right here, everything will come out in the wash. You don't need to do any adjustments then. So the formulas are set up so that you just plug in the load that's axial load that's applied to the bar, and you plug in the angle measured counterclockwise positive from the standard cross-sectional plane and the standard cross-sectional area. That's all you got to plug in. All the other stuff is in there and it just comes out for you, okay? So if I want to find the normal stress on that plane AB, I just plug in negative 6,000 cosine of negative 64 squared. Notice the negative is inside the parentheses there, okay? And then divide by 25. And I can't remember what that comes out to be. All right, when you run those numbers, it's negative 46.1. I'm kind of a little short of space here. I'll just put it in here. Okay, so there's the normal stress. And then the shear stress is negative, which is part of the formula. The load then is negative 6,000. So it's negative 6,000. Times sine of twice the angle, so twice negative 64 is negative 128, divided by 2 times the standard cross-sectional area. And there's the shear stress on plane AB, okay? So that's working through that problem. So that problem has a lot of conventions in it to kind of be concerned about and to enter properly. And that translates into the stuff we're going to do with biaxial stress too. There's lots of conventions that you have to pay attention to on those two. Okay, the last one was this load here. So we have this water tank, and we need to figure out the size of the column, the standard cross-sectional area of the column, so that it'll be strong enough to resist the stresses here, or that it'll not exceed, that might be a better way to say this, not exceed these stresses. Okay, now one thing on this is there isn't any tensile stress in the column, so you don't need to worry about the allowable tensile stress because there isn't any tensile stress. So the idea there is you're just getting information about that material and you're going to use it to design this column. That's just the information you're given, and then you just use that to design it. So that material does have a tensile stress, but we don't need to worry about it because the column is not in tension. It's either in compression or shear. It's in both, and we have to test both cases. Okay, so when you work through the total weight on this thing, what you get, and I'm sorry I'm a little messy here, but the weight is 107,000, or excuse me, it's 114,027 pounds. Now that's the weight of the water plus the tank, okay? So 114,027 pounds. Now the easiest way to handle that safety factor that's given of 1.5 is to factor up the load, which would be the weight. So that's where I applied that safety factor. And I got 171,041 pounds, okay? If I design this thing for that load, that includes the safety factor, okay? So what I do is I just use these two equations, and then I'll rearrange them for the area because I know the load, it's 171,041. I know the allowable tensile stress, or excuse me, compressive stress and shear stress. What I don't know is the area. That's what I want to do to design that column. So I'll just use A as P over sigma max for the allowable normal stress. So the P is the load, sigma max is given up above, and if that's the case, the maximum, the required area there is 47.5 square inches. Here's the formula for shear stress for an axially loaded bar. Solve that for A, it's P over 2 tau max. So P is 171,041, 2 divided times 1,500 goes into the denominator there, and I get 57 square inches. So this governs, okay? When I'm designing something, I take the bigger of the two sizes. So I'm going to go with 57 square inches there for the required size of the column. Take the square root of that, and I'll get 7.55 inches. That's the required lengths or the dimensions on the square column, so I'll round that up. So the square column then will have 8 inches on either side. Now another little thing came up on this. If you're gonna, now I suggest applying the safety factor to the load. Okay, that's the simplest way to do it. If you were going to apply it later on, you could have done that, but it's important that you apply it to the area. Okay, so, and I don't have a calculator here right with me, I don't think, but if you did that, that would be fine, and you would have gone with something like this. So if you wanted to apply the safety factor later on, not to the load, but to the size of the column, the proper place to do that would be the area of the column. Okay, that would be where you would apply that. All right, now if you had used the regular weight, the unadjusted weight, the 114,027, would have gone like this. So you would have had 114,027 pounds, and then you would have divided that by the 3,600 pounds per square inch. This would have been for the normal stress, so that would have been 114,027 divided by 3,600. And that would have been 31.7 square inches. And then had you done that again for the shear stress, that would have been 114,027 pounds divided by 2 times 1,500 pounds per square inch. And that would have been 114,027 divided by 3,000 there, and that would have been 38.0 square inches. Well, you would have taken the bigger of the two, and then you would have adjusted that by 1.5 for the safety factor, and that would have got the 57 square inches, okay? And that's how you would adjust that. Now, there were some people that made an error. They took 38, and then they took the square root of that to get the side length, because it's a square column. So they took 38, and they took a square root of that, and that was 6.16 inches. And then they said, okay, I'll multiply that up by 1.5, and that got a little bit more than 9 inches, 9.25 inches, okay? But that's not correct, because what you're doing then is, see, it's a square column, so you're using that safety factor twice, essentially, is what you're doing. So you're ending up with a much larger safety factor. This is the proper way to do it. You scale up your area. You don't scale up the dimensions, because there's 2 dimensions. So essentially what's happening then is you're ending up, when you do that, with an area of 85.5 square inches, which is too big. You don't need that. So the proper way to apply that safety factor then would be to the area, okay? Just thought I'd mention that. All right, now we have a couple problems that are due on Friday, 191 and 2. I just thought I'd go through one of them, which is 191. Okay, so let's have a look at that. Now 191, this is a typical biaxial type problem. Now what you want to do with this is, when I'm starting these, I fill in, before I start, I fill in this table basically. I fill in the values for sigma x, sigma y, tau xy, theta, and 2 theta. That gets me started. From there on, it's just plugging stuff into equations. All right, so we can just go ahead and fill that in. All right, so sigma x is right there. That's negative because it's compression, 18,000. And then sigma y is right there. That's negative, again, compression, 4,000. Now, tau xy, what that is by convention is the shear stress on the vertical plane, because that's called the x-plane. So you're using that shear stress right there every time. I mean, that's the definition of that number. When the equations here were derived, they were derived using that shear stress. So that's going to be 2,000, as you can see. And then what you want is the sign on that. And as we've gone over a couple of times now, if I put a nail in this, if this is a board nailed to the wall, what that shear would do would be to rotate it counterclockwise. So that'll be a positive 2,000 there. Okay, so when you run these formulas, you always use the shear stress on the vertical plane for tau xy. Okay, similarly, theta is the angle from the vertical plane, okay, and it's measured counterclockwise positive. So regardless of what angles I'm given here, the one that I would use would be 60 degrees, and that'll be positive because it's counterclockwise. And then I like to get 2 theta because that's what I put into the formula. Okay, so there's the information that you'll put into the formula right there. And when I'm doing these problems, I like to collect that and put it on the top, then I just plug everything in. It just cuts down on the errors that I might make, okay? So there's the data I want, and then I'll just go ahead and plug all that in. All right, so I'll run that first. We're using those numbers. I'll run the equation the first time. I'll plug that stuff in, and I'll get the normal stress at 60 degrees. It's negative 5768. Okay, then I'll run those numbers a second time for the other plane. See, that's the shear stress on AB, on that plane, okay? So that's sigma AB. Now, if I want to get the normal, that's the normal stress or axial stress on AB. If I want to get the axial stress on BC, what's going on there is I've got 60 degrees from the standard reference plane, the vertical plane, to AB. Well, that element there, ABC, is a square, so that angle ABC is 90 degrees. So if I take 60 degrees and add 90 to it, that will get me from the standard reference plane, the vertical plane, counterclockwise, to plane BC. So if I take this angle of 60 and add 90 to it, I'll get the angle to BC. When I double that, I get 300 degrees. I can plug that into the formula and get my second stress, okay? Now I can call that 2 things. I can call it sigma x1 for 150 degrees, or I can call it sigma y1 for 60 degrees. I can call it either one I want. They're equivalent things, okay? And that comes out to be negative 16,232. Now, if that's one way to do it. Now, another way to do it is just to use the shortcut formula, okay? So that shortcut formula is on your formula sheet. It's formula 31. Okay, so once you have sigma x1, which we got for the plane AB, I already have got sigma x and sigma y, so I can just plug everything in and solve for the last unknown, which is sigma y1. That's another way I can get this answer. Now, if I have this formula programmed, I'll just go ahead and plug in those angles and get and plug in the 150 into my spreadsheet or my program on my calculator or whatever, and I'll kick this out. That's easy. But if I don't have a programmable device, like as will be the case when you're taking the test, because you can't use a programmable calculator on the test, I would then use this formula because it's quicker, okay? You don't have to do all the trig and things. All right, so that gets you the normal stress on plane AB and the plane BC. Okay, now the last thing to do is to find the shear stress. This is on the plane AB again. I'm going to plug in these same values, and I'm going to plug in theta equals 60, okay, because I'm going to use that to find the stress on plane AB. So I'm using those values for sigma x, sigma y, tau xy that I had up above. I'm using these values. Plus, I'm also using the 60-degree angle, okay, because I want to know what the shear stress is now on plane AB. So I just plug all that stuff in, and out comes a positive 5,062 psi. All right. So now I've collected all that information. What I'd like to do now would be to sketch this up so I have some idea what's happening at that particular angle. And there you go. So there's the sketch. So what I've got on AB at 60 degrees, I came up with negative 5768. The negative means compression. 90 degrees further, which is 150 degrees, I got a normal stress of 16,232. So, and that's negative again, that's compression. And then also I got a shear stress on the 60-degree plane, so I marked the wrong one there. It's right here. That was a positive 5,062. So I draw this one in positive because if I nail that board to the wall, that stress will rotate that thing counterclockwise, which is positive. So that's the positive shear stress on AB right there, positive. Now the other shear stress here meets in the corner, so the two arrowheads go together at the corner. And then the other two shear stresses are on the other side, and they meet at the opposite corner. So that's how those shears act at that angle. Okay, so now what I've got is a nice sketch that's showing me what the stresses are at these particular angles for this element. I only label one side, so I just put 3 labels on there, you know, because we know that this stress is also equal to 5768. We know that this stress is also equal to 16,232. Those are both compressive stresses. And we know that all 4 of the shears are 5,062. All right, now another thing that I have available to you is a spreadsheet that will calculate biaxial stresses for you. You can just download that if you want. You know, this is a very repetitive task. It's kind of a complicated formula. You know, there's room where you can make errors here. So by using a spreadsheet or by programming your calculator, you can cut down on the errors. So that spreadsheet will look something like that. So what you do is you just plug in, you know, whatever the values are for sigma x, sigma y, and tau xy. And actually it's negative 18,000. So let's go ahead and put that in there. We've got sigma y is negative 4,000, tau xy is 2,000. Plug in the angle you're interested in, it will tell you what sigma x1 is, which is negative 68 actually. Now, I didn't quite label that right. That should be sigma y1, which is 90 degrees off of sigma x1, and that's negative 16,232, and then the shear at the angle of 60 degrees is 5,062. So that's a tool you can use. If you use this on your homework, just put a little bubble and say use the spreadsheet or something so I know how you calculated. Keep in mind though, on a test you do have to calculate things manually. All right, so this gets you the same answers as we just showed you there, as I just showed you there a minute ago. So it's just running these equations and getting these answers is all it's doing. All right. All right, that's just a run through 191. 192 is quite similar. And remember to include the sketches when you turn that homework in. All right, the last thing here, let's have a look at an example. And I don't think I've got this in your book, so you'd have to go ahead and just write this one up, okay? All right, so here's an example. So why don't you sketch that up? And then, as I've mentioned, fill in these values. So you want sigma x, sigma y, tau xy, and then you want the angle. And then usually, if they're going to calculate it manually, I find 2 theta also, because that's what I plug into the formula, as you can see below there. So why don't you just pause the recording for a second and fill in sigma x, sigma y, tau xy, theta, and 2 theta. So just pause that for a second, do it, and then check back, and we'll run through them. All right, let's have a look now. Hopefully you've done that, so let's check that. So what we've got there for sigma x is negative 40 because it's compressive. That's this one. Okay, and then we've got sigma y is positive 310 right there, so that's positive. And now we've got the shear. Now for the shear, remember to always use the shear on the vertical plane. That's going down. It has a magnitude of 190. And if I put a nail in that board, that shear will spin the board clockwise, so that's going to be negative 190 megapascals. All right, so there are the values. Now I also want to find the angle. Now the angle by convention, and this is just how the formula was set up when it was initially set up, 150 years ago, is from the vertical counterclockwise positive, so that would be 120 degrees. Twice that would be 240 degrees. Now, if you wanted to, you could use the other angle there, the 60, that's coming from the proper vertical plane, but it's clockwise. So that would go in as a negative 60. And then twice that would be negative 120, and that's what you would plug into the formula. Now, you could use either angle, and if you think about kind of a unit circle or whatever the heck you want to call it there, 240 is right there. That would be this line. And that would be negative 120. So 240 and negative 120 are the same angle. They're just two different ways of calling it out. So you can go ahead and plug in either angle into the formula. So why don't you run the numbers? You could use that spreadsheet if you like, or you could calculate it manually. So just pause the recording, run the numbers, see what you get, then we'll check back in, okay? All right, so if you've run the numbers, let's have a look. They look something like that. So we're putting these inputs in. So there's sigma x1, I've got 387. Tau x1, y1, I've got negative 56.6. So those are the stresses on plane AB using these inputs. All right. Now, we got a couple things going on here that I want to mention. If we've got all those numbers worked out, you might be wondering why we're doing this. And there's a couple reasons on this example I can illustrate to you. For starters, though, why don't you go ahead and sketch up what you think is happening on plane AB, because that's what we just calculated is what's occurring on AB. So let's go ahead and see if you could draw a sketch of that. So if we know that we have those stresses in the x and y directions, and we know we've got some plane here that we're concerned about for some reason, plane AB, and that's making a 120 degree angle with the vertical. What are the stresses on that? What do they look like, okay? Because keep in mind, once you start working, you're going to be very concerned about what you're analyzing, what you got to look at. You got to be able to visualize this stuff to kind of understand the things you need to be concerned about when you design things and how to design them properly. So why don't you sketch up what you think that would look like, what's happening to that plane AB, given the answers that we got down below, all right? And again, you could pause the recording and do that, then we'll check back in, okay? All right, so there you go. I've got that little sketch up here. Now what's happening is on that plane, we've got tension of 387. So there would be a stress of tension 387 pulling both directions on that angle, on that plane. You might think of that if that was a board. That might be the way the grain of the wood is running. We might be worried if that grain can handle these stresses, given what we know to be the x and y stresses. We might say, okay, what's happening along the grain? And that's one reason why we might do this. Okay, and so what's happening on that plane is it's being pulled apart with a magnitude of 387 megapascals. And also, in addition to that, there's shear acting on that plane. Now that's a negative shear. So when I'm drawing up these shears, I think of them, when I draw them up, as kind of like couples. That helps me to visualize how to draw them. A negative couple on that plane would look something like that. See, that's negative because about the central point, it'll spin clockwise. That's why it's negative. So I put that on either side of that plane there. So this is what's occurring on that plane. And then if you knew about your wood and knew about the strength along the grain, you could then analyze and see if, your board was strong enough to handle that, okay? Now, the other thing I want to mention about this is that here are the stresses that we came in with. 310 tension in the Y, 400 compression in the X, and a negative 190 for the shear on the X plane there. Now, if you're designing this, whatever this happens to be, what you might say is, okay, I just got to design for a tension of 310 megapascals. That's what I need to design this for, okay? But if you look at the answers we got, that's not correct, okay? You've got to design for more than just this applied stress of 310. There's more going on inside of that plate, because if you look at that, that's bigger than 310, okay? So even though the largest stress in the X and Y direction is 310, when we look at the effects of all three of these with these equations and look at the stress that's happening at 120 degrees, it's greater than 310. Okay, so notice that's why we do this biaxial analysis, or it's one reason. If we're designing that plate and we know these are the X and Y stresses that are applied, we still have to go in there and look at different angles and try and figure out what the greatest stress is at a particular angle, okay? We're going to be interested in knowing the absolute greatest stress in that plate so we can design it to withstand it. And if you just pick 310, because that's the biggest of your applied stresses, that's not big enough. See, this thing goes to 387, maybe even more at a different angle. So we have to investigate that and come up with what are called the principal stresses, which are the maximum stresses acting in that plate. And those principal stresses are formed by running those equations for a combination of sigma x, sigma y, and tau xy. So that's the next thing we'll look at next time, is finding the absolute maximum stresses which you would design the object for and figuring out what angle it would act at.